I think you hear me. Okay. Thank you so much. So I will talk about a similar topic that Bence talked about, but we don't use, in this case, we don't use fermions, we will use bosons. I did this work with Bence and also Miha Osmanyek, Csankonó, and Zoltán Zimborás. First, I will talk a bit about photonic quantum computing. Then I will tell you about how to adapt these board machines, these quantum generative models in the photonic setting. Then I will introduce the model which we devised, these Gaussian bosonic board machines, which is based on a particular photonic quantum advantage experiment. And then I will demonstrate some numerical experiments. So photonic quantum computing, it stores information on independent optical modes called Q modes. So here you can see that there are some quantum light sources. For example, these can be single photons, which go through some optical processing. And for example, at the end, you can have single photon detectors, which detects whether or not there is a photon in the detector or not. And this is like a very rudimentary version of photonic quantum computing, or example of photonic quantum computing. Why do we want to use photons? They have stable coherence, they are fast, so there are many optical elements that operate on room temperature, and they are compatible with existing technologies, but there are also many downsides to it. One that I would emphasize that non-linearities are difficult to realize in a photonic setting, yeah, universality is hard to achieve. So here is a comparison to qubit-based photonic quantum qubit-based quantum computing versus photonic quantum computing. The main difference is here that while in a qubit-based quantum computer, the Hilbert space is a finite dimensional Hilbert space. In photonic quantum computer, even a single Q mode has an infinite dimensional Hilbert space, and the basis in this Hilbert space can be given by the basis 0, 1, 2, 3, etc. And it goes to infinity. And it has different kinds of elementary gates, different kinds of measurements. It's very different. So these Q modes can be modeled by quantum harmonic oscillators naturally. So 0 corresponds to the vacuum state, 1 corresponds to a single particle, and so on. But these can also be these photonic quantum states can also be described by distributions, quasi-distributions over the phase space, which is the Wigner function essentially. This can go to negative. That's why it's called a quasi-probability distribution. Yeah, this is very good to visualize photonic quantum states. And there are a specific class of states, photonic quantum states, which are the Gaussian states. These are completely characterized by its first and second moments. Yeah, this is not important, these notations. And the photonic quantum state is Gaussian when, if and only if its Wigner function is a Gaussian distribution with these displacement vectors and covariance matrices. Yes. And why is this important? Because there is a photonic quantum advantage experiment, which is called Gaussian Boson Sampling. It uses this setup. It uses Gaussian gates, and it produces Gaussian states in the end. And at the end, the Gaussian state is detected by a photon detector so that it yields photon detection samples. And they did this experiment already in 2019 with 100 modes and 76 photons. At the time, it was said that it was a quantum advantage because there were no algorithms which could, in reasonable time, execute this algorithm on a classical computer. But then later, such algorithm was published. So they repeated this experiment many times. And this new experiment was done in 2025. It's a much larger scale experiment. And this is important because it shows that this Gaussian boson sampling is very much scalable. It's a very scalable photonic quantum advantage scheme, and we want to utilize this. Okay, so now let's talk about Bohr machines in the photonic setting. So what is photonic quantum machine learning first? Yeah, what you expect is that we use these photonic quantum computers and photonic quantum states for machine learning purposes. It has all the advantages of photonic quantum computing, plus additionally, we have a high dimensional Hilbert space, so we can expect high expressivity, although not guaranteed. We may get possibly interesting distributions for generative tasks. And here is an example on such a photonic quantum neural network. This is called the continuous variable quantum neural network. It's called continuous variable because in photonic setting, you have observables which has continuous spectra. That's why it is called like this. So it uses linear gates plus some nonlinear gates. This Kerr gate denoted by K, which is a nonlinearity. It's quite difficult to implement experimentally, but it makes this neural network universal. So this has high expressivity, universal, but it has trainability issues because such a thing you need to train on a quantum computer. And Kerr gate is also difficult experimentally. There is also a thing called continuous variable Born machines based on this quantum neural network. So we train a variational quantum circuit to learn a probability distribution, and we use homodyne measurements at the end. It is very natural for continuous distributions, but the gradients are still expensive. It's very difficult to train. It still requires Kerr gate to be not easy to perform on a classical computer, and you cannot really learn anything than a quantum distribution, meaning that a distribution generated by a quantum computer. So it might not be that useful. So here is an example on how to, or what it looks like. So this is a very small scale experiment of a continuous variable Born machine. Yeah. And now let's talk about Gaussian bosonic Born machines, which unifies these principles of quantum machine learning, photonic quantum machine learning, plus Gaussian boson sampling, plus the classical trainability, which Bence has talked about earlier. So the idea is, yeah, what I've said, that we use Gaussian boson sampling, classical trainability, and generative modeling. This is good because Gaussian boson sampling is classically hard. It's very similar to the quantum advantage experiment that Bence talked about, the fermion sampling, but it is based on bosons, or specifically photons in our case, instead of fermions. It is feasible experimentally, highlighted by the experiments that I have shown you. It may have high inference throughput because photons are fast. So we expect that the inference will be very fast in these machines. But there is a challenge that we need to find a good observable. So Bence used Z operators. Here in the bosonic setting, there is no direct analog of a Z operator here. So what do we require from this observable so that it's easy to obtain the expectation values classically, has binary outcomes, and correspond to experimentally feasible detection schemes? I will talk about one now, this parity detection. So it distinguishes during the particle number measurement between the even and odd particle numbers. And it's really easy to evaluate, at least classically, although there are downsides to it. The second one is threshold detection. I will not talk about this due to time constraints. So these parity expectation values, as I've said, it's really easy to compute for a Gaussian state on a classical computer. It uses this very simple formula. This is essentially proportional to the central value of the zero value of the Wigner function. And because the Wigner function is a Gaussian function or a Gaussian distribution, it is really important to apply displacements because then it would shift the Gaussian distribution so that you can get values that are not close to 1, basically. We executed some numerical experiments with this. So this is based on this numerical experiment. This is a small-scale numerical experiment based on handwritten digits. This is 16 by 16 handwritten digit data. And we executed a similar benchmark that Bence has shown before. And you can see that we compared with classical models such as the Choliu model, and this RBM is the restricted Boltzmann machine, and this GBBM is the Gaussian bosonic Born machine, which I've talked about. And you can see that at least on the second order, these are the covariance matrices, which Bence has also shown. At least on the second order, this is a very good fit to the test set. And also, if you look at the maximum mean discrepancy value, this is also much better than the restricted Boltzmann machine, for example. So yeah, this is a 16 by 16 data, so it's 255 modes, 56 modes. But this genomic training was executed on 805 modes, and we used over 1 million trainable parameters. And I think at some point this was a record in the number of trainable parameters. We also compared this experiment with the Choliu and the restricted Boltzmann machine, and it also performed better here. And we also executed training on the Ising dataset using threshold GBBMs, but because I didn't talk about the threshold, I don't talk about this. And we also looked at the effect of the overparameterization in this case, similarly to, as Bence demonstrated in the fermion sampling scheme. It's apparent that if we overparameterize, then we get better results. And an important point is here that, of course, so we can overparameterize, meaning that we can put several layers of interferometers classically in this scheme, but at the end, because it's a Gaussian state, we can compress it. So at the inference stage, we don't get a more difficult experiment if we do this overparameterization, and that's crucial. Oh yes. So as a conclusion, so Gaussian bosonic Born machines offer the following: classical trainability, meaning that you can do the training on a classical computer and you don't have to do it quantumly, so that we can so that it is experimentally more feasible. We don't have sample efficiency issues and anything. These guarantees, I mean, there are some guarantees on hard classical sampling. So if you sample a random interferometer, of course, like the sampling on a classical computer is hard. With training, it's unclear, but at least there is some hardness guarantee, and it's also experimentally feasible, as I have shown you. And there are some further directions, for example, using non-binary outcomes, for example, also continuous outcomes, similar to the continuous variable Born machine that I've shown you. Maybe we can use more expressive observables, not based on the parity, and not based on the threshold detection, but other detection schemes. The addition of non-Gaussianity. So in this Gaussian bosonic Born machine, there is no Kerr gate and there is no nonlinearity. But if we can add some nonlinearity or non-Gaussianity, that would increase the expressivity of the model. And also, what we want is to identify the boundary between the enhanced expressivity and the classical interactability on these models. We are working on all of these currently. Thank you so much.
Thank you very much, Zolin. And time for questions.
Hi, thank you for your presentation. It was pretty cool. I really liked how you showed the training of the numbers as well. But yeah, I had a question on scalability. So how well does it scale if you start increasing parameters, like the number of parameters that you want to train or that you want to infer?
So in the number of parameters, so the question was how the classical training algorithm scales with the number of trainable.
the inference on the quantum side, right?
So in the inference stage,
Yeah.
with the trainable parameter. Well, so if you don't scale the number of modes and you scale the number of parameters, then at the inference stage we don't have any more complexity. So as I said, if you would, okay, so let's say that you have an interferometer, like a layer consisting of a squeezing gate and an interferometer, and if you add another one in the classical training, yeah, you have more trainable parameters. It's more difficult. But at the inference stage, so these two layers can be compressed into one layer. So it's the same, basically.
Okay, and then so if you increase the number of modes, that then scales your your machine basically linearly as well.
Yeah. So if you increase the number of modes, then you have to add more inputs and you have to add more beam splitters and optical elements and yeah.
Okay, yeah, thank you.
Okay, Tony.
How specific are these methods for photons? So, for example, other bosonic ions or phonons even. Can it be repeated, these things?
This is not specific to photons, although so this is it is most feasible experimentally with photons as far as I know. Yeah, I don't know about phonons, or I don't know. So the problem is that can you detect the parities? So like that you can get that you get even number or odd number of photons or excitations. And in the photonic setting, there is such a way, of course. I don't know about phonons or any other bosons.
Any further questions? If not, then I would have one. So you mentioned that one of the future direction is the non-Gaussian.
Yes.
Can you say something about that how you can manage this? So what are the opportunities with this?
Yeah, so with the non-Gaussianity or non-linearity. So the problem is that if we consider like this, can I go back? Maybe not. So if we add, so this is a Gaussian boson sampling setting. This is what we have to repeat experimentally. So the problem is with there are two problems. If we add the care here, then it's unclear if it is classically trainable. So we increase the expressivity on paper, but it is not clear how to train on a classical computer, and then we have to go back and train on a quantum computer, which is we don't want. But maybe there is some algorithm which makes it feasible. If we don't use photon detectors, but maybe we do homodyne detection as we did for the continuous variable Born machine, and if we add care there, maybe or there is a possibility that we can classically train still. And also, like the problem with the nonlinearity is that it's not experimentally feasible. Not many people implement care gates. There are other ways to add nonlinearity. For example, what you can do is that you have a mid-circuit measurement, and in this mid-circuit measurement, you detect the number of photons, and then you immediately inject back the same photon. Apparently, it does nothing, but it destroys some quantum coherence. And this is a nonlinearity which can be used to increase the expressivity, although it's unclear how to make it classically trainable. Yeah.
Okay, good luck. Thank you very much. Okay, let's thank Zoli again.